All right, so we've talked a little bit about confidence intervals for means. So trying to estimate the population mean given a sample with continuous or continuous-like data. But let's also talk a little bit about proportions. So if you remember, a proportion would be just like a percentage. So if you think about a poll, that would probably be the most common application of thinking about proportions. We ask people a yes or no question, or we ask people, are you voting for X candidate in the presidential election? And some number of people say yes, and some number of people say no. So we can report the proportion of people who are voting for this candidate. Or in biostatistics, you might think of that more in terms of, what percentage of people, are hospitalized from COVID-19 who have symptoms. So, if you're showing symptoms, some percentage are going to need hospitalization, some percentage are not going to need hospitalization. So, right, those are proportions. And oftentimes, all we can do is collect a sample and try to estimate those proportions using our sample proportion. So, just like with means, we can create a confidence interval for the true proportion and center it around our sample proportion, which is going to be our best estimate for that true proportion. And so we're going to follow a process that's pretty much identical to what we did with means, but there's two changes we have to keep in mind here when we're working with confidence intervals for proportions. The first change is that our assumption, our central limit theorem related assumption, looks a little bit different. So when working with numeric data, we have to have either a relatively normally distributed population to begin with, or we have to ensure that our sample size is sufficiently large such that the sample means are going to distribute normally. Well, with proportions, we don't really have the same problem. Proportions data, so yes, no data, and we're just counting what percentage out of the total said yes. If we think about the distribution of possible sample proportions, that distribution will distribute normally pretty much immediately, even with a very small sample size, because there isn't exactly a population shape. The population shape is just two columns. It's a column of people who say yes and the column of people who say no. And when we take a sample proportion, the distribution of possible sample proportions we could get does distribute in a normal fashion, as we'll see here in this sim. What we do have to make sure is that our distribution of sample proportions is centered far enough away from the floor, which is 0%, and far enough away from the ceiling, which is 100%. So to demonstrate what I mean by that, I have Plinko probability open here, which is a sim that I have actually worked with and done some research with this group called PhET. So what I'm going to do is I'm going to get just a large number of rows. I'm going to set my population proportion to 50%, meaning that there is an equal chance that the ball could bounce left or bounce right every time it hits a peg. And so every time a ball lands at the bottom, it's kind of like a sample proportion. It's the proportion of times out of 25 rows that my ball bounced right. So most of my balls are bouncing around the 11, 12, 13, 14 range. Some are dropping a little bit farther away. So this is my distribution of possible sample proportions given a sample size of 25. And you'll notice that this shape is relatively normally distributed, right? So it's working pretty well. I'm pretty far away from either edge. But you'll notice something is that if I were to set this binary probability farther to 100% or farther towards 0%, I would actually run out of room here. So even though I'm going to stop this here because I'm going to switch this binary probability to a much smaller number like 8%, and you're going to notice that the distribution of possible sample proportions is not going to quite be normally distributed in this case. And that's because I don't have enough room for that distribution to fully become symmetric here, because it literally runs out of room here because I can't get sample proportions below 0%. So if I were to let this run for longer, you would see that more distinctly. But you can already kind of tell there's going to be a little bit of a right-skewed distribution emerge here. I'm going to see this distribution isn't going to fully become symmetric. Instead, it's going to kind of extend right skewed out, stretching this way. All right, so we'll go ahead and stop it there. My mouse is kind of dragging there. I got too much going on with the screencast recording. I'm going to switch back over to the notes. So that is the assumption that we're going to need to make here, that in order for my distribution of sample proportions to be normally distributed and for me to use these confidence interval properties that I'm using, then we should have at least 10 successes and 10 failures in our sample. In other words, we should be far enough away from either edge that our distribution should be normally distributed in that case. So as long as our sample size is sufficiently large, right? So if I have a sample size of like, 300, 500, even if the true proportion is really small or really large, like 2 or 3% or 97, 98%, as long as I have at least 10 successes and 10 failures in there, I'm probably going to be okay. I probably have enough room there. But yeah, that is kind of our new assumption in place of the sample sizes greater than 30 point that we normally make. The second thing that we have to watch here is that we are still using our sample standard deviations to the population standard deviation. However, it's actually acceptable for us to go ahead and create a z-interval when we use proportions. And it has to do with the fact that the range of possibilities for our standard deviation is going to be limited between 0 and 0.5 when we work with proportions. It kind of maxes out at 0.5. So that means that our sample standard deviation cannot be off by too large a margin. There's kind of a cap there for how far off we could possibly be. So typically if you're using software, software can make a small adjustment in your standard deviation in this process such that the z-interval is actually going to be fine. So we're not going to delve any more into that idea than this, other than just to say that if you do an interval with proportions, you can use a z-interval. If you're using software, use a z-interval. It's totally okay. Thus, we have the formula. We're going to start with our sample proportion as our best estimate, plus or minus the relevant z-value for the confidence level we want, times the standard error for our sample proportion.